The double and add algorithm for computing scalar multiplication is perfect. Let's think about scalar multiplication for a second. Imagine we have 7 you multiply a point by 7. That means that we add a point to itself 7 times. So that's p plus p plus p 7 times. And if we have 37, that means we are adding a point to itself that 7 points that 6 times. And so that's so many times. So when there are only two things that you can do on an elliptic curve, which is addition and doubling. So addition is when you add 2 points on a curve, which is like p plus q. P and q are different points. And then there's also doubling. Doubling is when you add a point to itself, which is p plus p. That is 2p. That is doubling. And using a combination of this doubling and adding is how we can achieve scalar multiplication, since the first adding a point by itself is just doubling the point, and then we keep adding the point till we get into a loop. But these scalars are usually big in elliptic curve cryptography. Scalars represent your private key for your cryptocurrencies and all that. So it's usually a very big number, 256-bit number. And if you add a number to itself this many times, it's going to be quite difficult. Every time you're making a transaction, you have to do this, adding a point to itself this many times. But there is an algorithm, which is the double NAND algorithm, which grows logarithmic in size to the scalar we are using. Logarithmic in size means that when you say logarithmic in size in computer science, so when we say something grows logarithmic in size, it means it doesn't grow as much, it doesn't grow too much. Like, for example, it requires 4 bits to represent 8, and for 2 power 256-bit number, which is a very big number, it only requires 26 bits to represent that number. So as compared to when a number when something grows linearly as something grows, logarithmic grows in a more forgiving fashion. And so as algorithms that grow logarithmic favor actions of a computer. I'm going to show you a new method of evaluating a polynomial. So when say evaluating a polynomial, say we have a polynomial that looks like this. This is a degree 3 polynomial. When we say evaluating a polynomial, that means that every time we see an x, we replace it with a 3. So this is going to look like this, and our answer is going to be 58. One method of doing this is where you line up the coefficients and then with the powers of 3, and then you multiply them and add them together, and you get 58. But this honest method of evaluating a polynomial is a way where you avoid doing like a power x power 3 or x power anything greater than x power 1. You are still going to do it, but you're doing it indirectly, and it has a lot of let me show you. When you see this polynomial, we would restructure it, add brackets to it. Simple. So it's going to look like 2x power plus 0. So we compute, this is the first part. And then we add, we're adding 0 because the coefficient that represents x is going to be 0. So we keep expanding x, and here we are evaluating power of x, which is greater than 1. And then also another advantage is like the coefficient that represents x here, the x power 2 here, which is 0. We don't compute its power because it is 0, and it didn't have any effect on the overall equation. And here we just adding 0, which is like doing nothing. So yeah. show you another example. Say we have 5x power 5 plus 3x power 2 plus 1. So this is a polynomial in which has every power of x, and it's just that some most of them are 0. So if we were to do this directly, we would do, let's say we are evaluating a 3, we would do the powers of 3, and then we would add them to get, multiply with its corresponding coefficient, and then we would add and get the final answer. But when we are doing the honors method of evaluating a polynomial, we are going to completely avoid doing the power of like 5 directly. So here we are going to start with 5 power x, 5 power 3, which is going to be 5 power, which is 15, and then the entire equation turns into like we do the brackets, and then every time we have the coefficient is 0, it means like we are doing nothing. We have it easy there, and we just multiply by another x, and here it's like we are reusing our work. I think the beauty of this method of evaluating a polynomial is you don't have to like do power of x, and then we are looking at which coefficients or which parts of the equation need a lot of work, and these are the ones with the high powers, and then we build them first, and then anytime then the ones that require less work we'll build them later. Turns out we can get to redo a lot of work that was in the polynomials, and so the reason we're doing this is to see like how it comes with the double and add algorithm. Any number that we do, like say we have 1035 is represented, it's actually a powers of 10. It's a polynomial in powers that is evaluated at powers of 10, where we have the thousands, hundreds, tens, and thousands, and ones. So these are the coefficients for here, but then we are evaluating at powers of 10, and this is the same for binary. So we have a binary like this, and this is also going to just be representing as the powers of 2. And so the advantage of having it as powers of 2 is that the only thing, since the coefficients are from base 2, they can either be 1 or 0. So what you'll do is add 1 or do nothing, and then when you are going to the next step, you multiply by 2. So you're just going to be adding and doubling and doubling. So multiplication by 2 in some places in the world is called doubling. And from the way we were looking at scalar multiplication, we treated, like even when we were saying 7p, we are treating p as 1. So it's like we say 7p, we are adding p to itself 1. So when we are doing scalar multiplication here we replace our 1s with p. And then so it's going to be doubling and adding a point to itself. So in this method, it depends only on the length of the bits. The binary representation, the length of the binary representation, and you double every time you move. You are going to be doubling, but you only add a point depending on whether it's a 1 or 0. So depending on the Hamming weight or the number of ones in the binary. And the reason this is perfect is because imagine with the only two operations that we could do on an elliptic curve was doubling and adding, and all of a sudden this doubling and adding is like being convenient. It's a way it gives us a convenient way that scales nicely for big inputs, and does not require us to do anything else other than what we're doing. It's like being given a diesel engine and being told, here is diesel, you're only allowed to run on diesel, and then you're given a diesel engine. It's like perfect. It's like a match in heaven. Yeah, and that's why the double and add algorithm is perfect. Though there are other improvements, which is like the GLV method, which is another way, which also uses double and add algorithm, but improves and makes us do less work, which is I hope we'll get to star on this channel again. I will take, maybe we can talk about that. It's a very nice way and lazy and a way of getting better at this double and that algorithm. Yeah, peeps.